In this final outcome, we explore the period 4 transition metals, the first row of the D block. We'll look at their electron arrangements, their variable oxidation states, how they act as catalysts, and how complex ions give rise to their famous colors. Let's place them first. The D block sits between groups 2 and 3, running through periods 4 to 7, and the period 4D block is the row from scandium across to zinc. As you cross that row, electrons are filling the 3D subshell, and that's what defines a D block element. Its highest energy electron is in a D orbital. One subtlety to flag now, though, is that not every D block element counts as a proper transition metal, and we'll see why shortly. Writing their configurations needs a little care, because the 3D and 4s subshells are extremely close in energy. The 4s subshell fills first, but by convention we still write 3D before 4s. So scandium is an argon core 3D1, 4s2, titanium 3D2, 4s2, vanadium 3D3, 4s2, manganese is 3D5, 4s2, iron 3D6, 4s2, nickel 3D8, 4s2. Two elements, though, break this tidy pattern: chromium and copper. Let's write a configuration for iron, atom, and ion. Iron has 26 electrons, filled in the usual order, giving 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2, or argon core 3d6, 4s2 for short. Now the important rule for ions. When they form, the 4s electrons come off before the 3d. To make the 3+ ion, we take both 4s electrons and then one 3d electron. That leaves 5d electrons, so iron 3+ is argon core 3d5, an incomplete d subshell. Here are the two exceptions. Chromium is expected to be 3d4, 4s2, but it's actually 3d5, 4s1. Copper is expected to be 3d9, 4s2, but it's really 3d10, 4s1. In each case, a single electron shifts from the 4s into the 3d. The reason is that a half-filled 3d5 or a completely full 3d10 subshell is especially stable, and that lower overall energy is what the atom settles into. Let's explain the chromium case properly. The 3d and 4s subshells lie at very similar energies, so promoting one 4s electron up into 3d costs very little. Doing so gives 3d5, 4s1, with every one of those orbitals singly occupied. That symmetrical half-filled arrangement reduces the repulsion between electrons and gives what's called extra exchange stability. Since that stability outweighs the tiny promotion cost, chromium adopts 3d5, 4s1 because it has the lowest overall energy. Now for a careful definition. A transition metal is a D block element that forms at least one stable ion with an incomplete D subshell, meaning the 3D is only partly filled, anywhere from D1 to D9. Iron is a perfect example. It forms iron 2+, which is 3d6, and iron 3+, which is 3d5, and both of those are incomplete. It's this partly filled D subshell that gives transition metals their whole set of characteristic properties. That definition neatly excludes two elements at the ends of the row. Scandium only ever forms the scandium 3+ ion, which is 3d0, an empty D subshell. Zinc only forms zinc 2+, which is 3d10, a completely full one. Neither ion has a partly filled D subshell, so strictly neither counts as a transition metal, and it shows in their chemistry both are colorless and both stick to a single oxidation state. One hallmark of the true transition metals is variable oxidation states. Because the 3d and 4s electrons are so close in energy, several of them can be lost, giving a whole range of stable oxidation states. The successive ionization energies rise only gradually across those subshells, which is what makes this possible. So iron commonly shows +2 and +3, copper +1 and +2, chromium +3 and +6. And manganese runs all the way from +2 up to +7. Let's put faces to those numbers because many are strongly coloured. Chromium shows +2, +3 and +6, manganese +2, +4, +6 and +7, iron +2 and +3, and copper +1 and +2. You'll recognise some of the species. The dichromate ion is orange with chromium at +6. The manganate 7 ion is deep purple with manganese at +7. Iron 2+ is green and iron 3+ yellow-brown. And copper 2+ is that familiar blue. A few definitions to anchor this. A D block element is one whose highest energy electrons occupy a D subshell. A transition metal is more specific. A D block element that forms at least one stable ion with an incomplete D subshell. Oxidation state is the charge an atom would have if all its bonds were treated as fully ionic. And a variable oxidation state is simply the ability to form ions of more than one charge, like iron 2+ and iron 3+. Let's check your progress. Can you write the electronic configuration of a copper atom and of the copper 1 ion? Can you explain why zinc isn't classed as a transition metal? And can you state 2 oxidation states shown by manganese and give an ion for each? Take a moment on those before we move on to catalysis. Transition metals are superb catalysts, speeding up reactions without being used up overall. A catalyst works by offering an alternative route with a lower activation energy. Transition metals are good at this for 2 reasons. Their variable oxidation states let them accept and donate electrons, so they can form intermediate species with the reactants. And their vacant d orbitals can absorb reactant molecules onto the surface and weaken the bonds within them, making reaction easier. There are 2 kinds to distinguish. In heterogeneous catalysis, the catalyst is in a different phase from the reactants, typically a solid catalyst with gaseous reactants that adsorb onto its surface. Iron in the Haber process is the classic example. In homogeneous catalysis, the catalyst is in the same phase as the reactants, usually everything in aqueous solution, and it works by forming an intermediate ion or complex. A good example is iron 2+ with the peroxydisulfate and iodide ions. Let's name some heterogeneous catalysts you should know. In the Haber process, iron catalyses nitrogen plus hydrogen coming to equilibrium as ammonia. In the contact process, vanadium 5 oxide catalyses sulfur dioxide plus oxygen going to sulfur trioxide. And in hydrogenation, nickel catalyses reactions like ethene plus hydrogen going to ethane. In every case, a solid catalyst provides an active surface where reactants adsorb, react, and then the products leave, or desorb. Let's see how vanadium 5 oxide catalyzes the contact process using oxidation states. In the first step, the vanadium 5 oxide oxidizes sulfur dioxide to sulfur trioxide and is itself reduced to vanadium 4 oxide, with vanadium falling from +5 to +4. In the second step, oxygen reoxidizes the catalyst, turning the vanadium 4 oxide back into vanadium 5 oxide and lifting vanadium from +4 back up to +5. Add the 2 steps and the vanadium cancels, leaving the overall reaction of sulfur dioxide plus oxygen to sulfur trioxide, with the catalyst regenerated. It's the variable oxidation state, +5 to +4 and back, that makes the catalysis work. Here's the homogeneous example in detail. The reaction of peroxydisulfate ions with iodide ions is very slow on its own, because both are negative ions and they repel each other. Iron 2+ speeds it up beautifully. First, the iron 2+ reacts with the peroxydisulfate, becoming iron 3+ and forming sulfate ions. Then the iron 3+ reacts with the iodide ions to give iodine, and in doing so it turns back into iron 2+. The ion cycles between its two oxidation states, so it's regenerated and keeps working. Now to complex ions, which are behind the colours of these metals. A complex ion is a central metal ion surrounded by a set of ligands. A ligand is any species with a lone pair of electrons to donate, and each one forms a dative or coordinate covalent bond to the metal, where both electrons of the bond come from the ligand. A textbook example is the hexaqua-copper 2+ ion, which is 6 water molecules arranged around a central copper 2+. Let's define the complex ion vocabulary. A ligand is an ion or molecule with a lone pair that bonds datively to a metal ion. A dative covalent bond is a shared pair of electrons donated entirely by one atom. A complex ion is that central metal ion together with its surrounding ligands. And the coordination number is the number of coordinate bonds running from the ligands to the central metal ion. Ligands differ in how many bonds each can form, which we call denticity. A monodentate ligand donates just one lone pair, like water, ammonia, the chloride ion, or the cyanide ion. A bidentate ligand donates 2 lone pairs from a single molecule, such as ethane 1-2-diamine, often shortened to N, or the ethandioate ion. And a polydentate ligand donates many lone pairs at once, the star example being EDTA 4-, which can donate 6. Remember that the coordination number counts the bonds, not the number of ligand molecules. Comparing them directly, water is monodentate with 1 bond, ammonia the same, so you'd need 6 of either to fill an octahedral complex. You see that in mixed complexes, like the one with 4 ammonias and 2 waters around copper. The ethanidioate ion is bidentate with 2 bonds, so 3 of them fill an octahedral complex, and a single EDTA 4- ion is hexadentate, wrapping right around the metal and filling all 6 sites by itself. The coordination number sets the shape. A coordination number of 6 gives an octahedral complex with 90-degree angles, as in the hexaqua iron 2+ and hexaqua copper 2+ ions. A coordination number of 4 is usually tetrahedral, with angles of 109.5 degrees, like the tetrachlorocuprate ion, though some 4-coordinate complexes are square planar instead. And a coordination number of 2 gives a simple linear shape at 180 degrees, as in the diamine silver 1 ion. Let's predict 2 shapes and explain the difference. For the hexaqua copper 2+ ion, we count 6 small water ligands around the copper, so coordination number 6, and 6 bonds arrange themselves to minimize repulsion into an octahedral shape. For the tetrachlorocuprate ion, there are 4 chloride ligands, so coordination number 4. The chloride ions are much larger and bulkier than water, so fewer of them can fit around the central ion. That's why this one is tetrahedral. The larger chloride ligands allow only 4 to bond. A quick check on complexes. Can you define the terms ligand and coordination number? Can you state the shape and bond angle of a 6-coordinate complex? And can you explain why a single EDTA 4- ion can replace 6 separate water ligands? Have a think, then we'll finish with colour. So why are transition metal complexes coloured? In a free metal ion, the 5,3d orbitals all have exactly the same energy. But when ligands approach, they repel the d electrons unevenly, and that splits the 5d orbitals into 2 different energy levels. In an octahedral complex, you end up with a lower set and an upper set, and the energy gap between them is written as delta E, or just delta. That gap is the key to the colour. Here's how the gap produces colour. An electron can absorb visible light and use that energy to jump the gap from the lower set up to the higher set, and the light it absorbs has an energy equal to delta E, following the relation delta E equals h times nu, where h is the Planck constant. Only part of the visible spectrum gets absorbed, and the color we actually see is the leftover complementary light. The hexaqua copper 2+ ion, for instance, absorbs red and orange light, so it appears blue. Let's calculate an energy gap. A complex absorbs light of wavelength 600 nanometers, and we want delta E per photon. We use delta E equals h times c over lambda, converting the wavelength to meters first. So 600 nanometers is 6 times 10 to the minus 7 meters. The top of the fraction, h times c, is 6.63 times 10 to the minus 34 times 3.0 times 10 to the 8, giving 1.989 times 10 to the minus 25. Divide that by 6 times 10 to the minus 7, and you get delta E of about 3.32 times 10 to the minus 19 joules per photon, which works out to roughly 200 kilojoules per mole across the Avogadro constant. Finally, what makes the color change from one complex to another? Anything that changes the size of the gap, delta E, changes the color. Swapping the ligands alters delta E. Changing the metal's oxidation state alters it too, so iron 2+ and iron 3+ differ. And changing the coordination number or shape alters it as well. And this also explains the colorless cases. Scandium 3+ is 3d0 with no d electrons to promote, and zinc 2+ is 3d10 with a full subshell and so no d2d transition possible. Both are colorless.